Welcome everybody to our colloquium of Wednesday. Today's speaker is José Hoyos from Instituto de Física de São Carlos, Universidade de São Paulo. And as usual, let me introduce a bit our speakers. So José did his, let's say, university career in Universidade Estadual de Campinas, and he got his PhD in 2005. His advisor was Eduardo Miranda, that we all know very well, in 2005, with a thesis on randomness in quantum speed systems. After that, he had a postdoctoral career in Missouri, Duke University, and finally MagLab. And after that, he came back to Brazil, and he became a faculty in São Carlos, where he is right now. His research interests are generally in condensed matter and statistical physics, and today's colloquium is about that, and is called From Disorder to Order and Disorder Again. José?
Thanks, Dario, for this introduction. Good afternoon, everybody. What I'm going to present today is in collaboration with Eric Andrade, which was a colleague of mine in São Carlos until recently. He just moved to IFSC-USP here in São Paulo. With Matthias Voita from Technische Universität Dresden, and my former master student. What is this? Well, I suppose I'll switch gears to the old-fashioned one. Michel Miranda, which now is a PhD student of Matthias in Dresden. So I will talk about two models, practically. One model is the G1, G2 Heisenberg model. And the other one is the pyrochlore, easy plane pyrochlores. I will try to be very slowly on that, why these materials are interesting, and why the physics of these materials are interesting. And mostly the physics that will appear is already here. And then when I switch gears, we use all the concepts that we have known to apply to this other material. Things will be fast when I talk about the easy plane pyrochlores. So they look like fancy. It's a fancy picture here. The concepts simplify everything. So what's the outline for today? Mainly, I want to talk about the effects of impurities in some frustrated magnets. Especially magnets that has these fancy phenomena that is known order by disorder. And order by disorder, there are many types of disorder, and I will try to explain what is the meaning of each of them. But the main topic here is that you have a frustrated system, and this frustrated system has a huge degeneracy in its ground state, and many sort of fluctuations will lift this degeneracy, like thermal fluctuations, quantum fluctuations. So this is what's called order by disorder. Thermal disorder will lift this degeneracy. Quantum fluctuations will do the same. And also statistical fluctuations like impurities will do the same. And we will see what's the physics coming out of this framework. All right. To talk about this order by disorder, I will tell you a little bit of the concept of vestigial order, which is some sort of order that resembles the usual, more conventional order, and I will define that precisely later. And we're going to see that when we add impurities in this framework of a frustrated system with order by disorder, many fancy, or not fancy, it's not a good word, many peculiar phenomena happen, like spin vortex instability that is induced by disorder. Disorder also induces what we call random mass and random fields. That's more conventional. And also induce some other type of dipolar-like fields, which I'm not talking about this one here. But You see the physics coming out of that. And on the easy plane pyrochlores even happen to appear another phenomenon called random access. So that's a bunch of words, not of much meaning so far, but we go slowly through all of them. All right, so that's the model. Let's think classically, for instance. We have a 2D plane where we have next nearest neighbor interactions, J1, J2. And I will say that J2 is positive, so J2 favors anti-ferromagnetism between the spins that they connect. So in this lattice here, something fancy happens, peculiar happens that is frustration, meaning that if I want to satisfy this interaction, I put these spins counter-aligned, but what I do with this guy here? If I align with J1, this other one is counter-aligned, and so the other way around. So you cannot satisfy all interactions, so that's somewhat frustrated, right? You don't satisfy everybody. Okay, so what happened in this frustrated system? Let's start slowly and go to this phase, this part of the phase diagram where I'm putting this axis J2 over J1. If J2 is very small, we can even put 0, for instance. We have a state that's called Néel state, where the spins form this crystal, this magnetic crystal, where if you know where one spin is pointing to, you know the directions of all the others. You can compute the ground state of these, the ground state energy of these.
Sorry, in this case, it's not frustrated, right?
Yeah, it's not. This is the not frustrated side.
Okay.
Yes, yes. Please interrupt me anytime. Okay. But then you can compute the energy. You get J1 of energy of this each bond, and you pay J2 if you slowly, let's say, increase J2 there. So that's the energy of this reference ground state. In the other limit, let's say, let's just erase J1, for instance. If you erase J1, you can see that you decouple two sublattices. You have the circle and the square sublattice, and they are not talking to each other because they talk via J1. And again, you have two Néel subsystems, and they are doing what they want to do. They form the Néel state in each sublattice. But you see that there is O3 degeneracy between these two sublattices because you can point out one sublattice to one direction and the other one to whatever direction you want. So there is this accidental O3 degeneracy happening there. But now if you switch on J1, let's say that I put J1 here, I gain energy because this is more or less counter-aligned. So okay, that's good. And I gain this energy here as well. But I lose the same energy here and same energy there. So if I switch on J1, nothing happens. And I have, even when J1 is not 0, I have a ground state that does not depend on this angle between the sublattices. And I stay with this O3 accidental degeneracy. All right. So if I compare this value with this value, the transition would be at 1/2. Of course, this is a very wave-hand argument, but this can be done very precisely. And 1/2 is indeed the precise value of this transition between this state and that state. Okay. So entropic selection, or order by thermal disorder. What that means? As I was mentioning in the beginning, these O3 accidental degeneracy between the two sublattices, the coupled sublattices, it's lifted by thermal fluctuations. At first glance, you would say, how come, right? It's not something that trivial. It's not energetic selection. It's not energetic. There is no energy that, by energy reason, meaning interactions that lift this energy. As we saw, it is degenerate. But there is a simple way to grasp the physics behind this entropic selection. Let's see. Now let's turn on temperature, for instance. And then this spin starts to wiggle around its equilibrium position. So the fluctuation is something very small. All right, so let's see what is the field seen by this middle one spin here. Well, it sees a static field because we have a static crystal that puts a field, so it's H naught. Let's not talk about them because this is simple energetics. What's more interesting is the field due to these fluctuations. So its own sublattice fluctuates if the fluctuation is very small. This fluctuating field is perpendicular to this static field. So that's this red arrow here that goes up and down in time. And of course, it sees also the other sublattices, and in this case, the fluctuations are a little bit tilted by theta. So it's this blue arrow here that is going up and down in time. So if I want to maximize the fluctuation on top of this middle spin, what should I do? I should align the fluctuating field 1 and 2. And this happens if theta is 0 or pi. With that, I increase entropy. And therefore, I diminish the free energy. Because free energy is U minus Ts. So I gain energy because T is now finite. And this entropy here should be a function of the angle between these two lattices. And if everything works perfectly, if this function is minimum at 0 and pi. So that's why I drew here cosine square theta. So this O3 ground state accelerator degeneracy is lifted down to Z2. Because now I can have the sublattice aligned or counter-aligned. That's the mechanism ordered by thermal disorder. And I think it's very beautiful and yeah. Yes.
And you say lattice, so it's two-dimensional. Sublattice is also two-dimensional. Sublattice.
Yes.
So it's layers of two-dimensional.
No, just one layer. So
each sublattice is two-dimensional.
Both of them. We have doesn't come back. That's our lattice, right? So you have a square lattice with nearest neighbor and next nearest neighbor interactions. And in the limit of J1 being 0, this circle sublattice is not connected to the square sublattice. So I have two uncoupled sublattices. So both are two-dimensional.
Okay, I understand. Okay. They're in the same plane.
Yeah, they're in the same plane. Yes, yes. Now you can couple by J1 these two sublattices and the energy doesn't change. You still have that a huge ground state degeneracy, which is lifted by thermal fluctuations. So it's an entropic selection, not an energetic selection. That's the key point that we have to keep in mind. If you don't believe in my wave-hand argument, there is a technical way to show that rigorously. The following sense. Now you parameterize all these fluctuations in terms of a reference state, which was that reference state that we were using up to now. And then that's your Hamiltonian 2D XY model. So I changed to 2D spins now. It works for 3D spins, but then you have to worry about an actual angle, but it's not important. So you expand for small fluctuations up to quadratic order, and then you can compute your free energy because now you can do the Gaussian integration, and you can Fourier transform and get the modes. So you see that to ensure that you have a minimum, this number here has always to be positive. And this to be positive, you have to ensure that the J1 is higher than half of J2. So that was 1/2 of the phase diagram I showed before. But nonetheless, you get an entropy that depends on temperature and the angle between the sublattices. That's your entropy, and you can plot it, and you see the cosine there. It's not exactly cosine square, but around here is proportional to cosine square, but that's it. Okay, sorry for this technical detail, but since we are having a school here, I suppose I should show that to the students. All right, so what the entropic selection wants? Remember, theta equals 0, so the two sublattices are aligned, or theta equals pi, they are counter-aligned. So theta equals 0 means that the state is ferromagnetic in the horizontal lines, but anti-ferromagnetic in the vertical direction. And the theta equals pi is the other way around. So I have anti-ferromagnetic horizontally and the ferromagnetic lines vertically. So that's what we argue so far, that the ground state actually would have this type of magnetic order, which is called columnar or stripe order. Depends on the school that you come from. But columnar or stripe, you see some paper, it means these two states here. So which symmetry this state breaks? Of course, it breaks the Hamiltonian symmetry, I mean the interaction symmetry, which is rotational symmetry of the spin. And also break the vertical and the horizontal direction symmetry of the lattice. So it breaks two symmetries. These O3 of the spins, and the symmetry between vertical and horizontal directions. So that's the symmetry that is being broken by this state. However, we know that at finite temperature, Mermin-Wagner theorem prevents that you break continuous symmetry in 2 dimensions at finite temperature if you have short-range interactions. So this state is not stable against thermal fluctuations. All right, but this state also breaks the Z2 symmetry of the lattice. So maybe this Z2 symmetry is really broken, the continuous symmetry, well, the continuous symmetry is certainly not broken because it is a theorem. But the symmetry between vertical and horizontal direction, can it be still broken? Because Z2 symmetry is a discrete symmetry that can be broken in 2 dimensions at finite temperature. So to answer this question, we have to come up with a clever way to investigate this. And to quantify this Z2 symmetry, we come up with a vestigial order. And in this case, it's called nematic order parameter, quantifying that this difference between vertical and horizontal direction. That is the following. Now look at a plaquette of our square lattice. And we know that these, now remember, I was not sure if I was clear, but I'm always now in the frustrated side. J2 is big. In that case, I want to be an antiferromagnetic in this red sublattice, and the antiferromagnetic is this blue sublattice. But it cannot have a magnetization in each sublattice because it breaks O3 symmetry. But now I will see, I will couple, not coupling, I will see how much one sublattice is aligned to the other sublattice. So I will propose this other parameter here. It's a scalar order parameter. It's not a vector. So being a scalar, if there is a symmetry breaking of this order parameter, this can happen because a scalar parameterizes a Z2 order. So what's the meaning of this order parameter? The meaning is the following. If it's positive, means that these two sublattices are aligned. If it was negative, it would be the other way around. So this picture here is to convey the following idea, that I do not break the rotational symmetry of the spins, but I do break the symmetry of this order parameter, this nematic order parameter. Meaning the following: if I compute this in a product, in each placket, I get a positive number. This is point to there, this minus this is point to there, this is a positive. The same thing here, the same thing there, and the same thing every placket. This minus this point there, this minus this point to the same place, and so it's positive everywhere. And this would be the state where that Z2 symmetry is broken, but not the O3 symmetry. It's a snapshot in space and time. So if you keep going here, these spins keep rotating. And if you take a picture from I don't know, 10 seconds later, these spins have all fluctuating, so the orientation will be totally different. But they will always be positive in each placket. Meaning the following: the two sublattices, they fluctuate, but they fluctuate together. So because the two sublattices fluctuate, O3 symmetry is preserved, but because they fluctuate together, this Z2 symmetry is broken. So that's the idea. So fluctuations preserve the local angle between the sublattices, but there is a Z2 spontaneous symmetry break. If they are in the 0 pi state, meaning that is mostly aligned,
sorry,
counter-aligned.
Microscopically, what is, because the two sublattices don't talk to each other, right? Almost.
No, I'm in the J2 side, big J2 side, but J1 finite.
I see. So that small J1 is what make the. I mean, because my question was
yes.
exactly, yeah.
Yes.
How do they know each other? Because there is a small J1. Okay.
Yes, J2 is very big, so you want to be more or less in an antiferromagnetic state in each sublattice. So they do that, but because of J1, they more or less fluctuate together. Yes, that's the idea. So an effective model for these nematic degrees of freedom would be the Ising model, because I have a Ising variable, so an Ising-like variable that is a scalar. And I could have interactions. Now the nematic degree of freedom is this number here in each placket, which can be positive or negative. So I have one placket here, and I have another placket there, and there, and there, and so on. So each placket has its own Ising-like variable. And this Ising-like variable interact with nearest neighbor and maybe next nearest neighbor interactions. Perhaps there is something else. But it's in the Ising universality class. So the Z2 symmetry transition, does it really happen? And it is in the Ising universality class. That's what I investigate by doing Monte Carlo simulations. So now you can put the full model in your computer, run it for as long as you can, and compute observables. So I'm computing that order parameter, the nematic order parameter, which is that inner product. I'm computing the specific heat, the susceptibility, and the Binder cumulant. The Binder cumulant is just this number here, which tells us that if there is a crossing of the Binder cumulant, this crossing, if the system is sufficiently large, happens at the critical temperature. I don't want to go in details, but if there is a crossing, there is a indication that there is a phase transition. We see the specific heat. If you increase system size, the specific heat keep increasing and develop some, I don't know, some divergence or so. And the same thing for the susceptibility. Of course, we cannot go to much larger systems because frustration hinders Monte Carlo simulations. But it's enough we could reach system size that's enough to do a finite size scaling of this problem. And we could collapse all the data, susceptibility and so on, using the critical exponents of the Ising model in 2D. So indeed, this transition that we saw by numerics is in the Ising universality class, even though these spins are all vectors in R3. You can compute the transition temperature for the many values of J2 over J1. When J2 over J1 is less than half, we would have that Néel state, which is destabilized by thermal fluctuations, so it's a paramagnet everywhere. And when you go to the frustrate side, then a transition appears. We have that singularities appear in the observables of the last slide. And that's the temperature. There is a critical second order phase transition to the paramagnet to a nematic state. All right, so that's it for thermal fluctuations. Quantum fluctuations, yes. No, if you shrink it to a ladder, then you have a 1D chain, Ising chain, at finite temperature. Yeah, but it's short range. To see a transition, you need long range, but that's not the case. They only have a Nielsen neighbor interaction, which is endowed from the original Hamiltonian, with short range interactions. All right. So quantum fluctuations. You can do some sort of spin wave approximations and arrive at the same conclusion. Mostly, you can do Hamilton-Jacobi equations. You compute the second derivative of this fluctuating field. And you get that same matrix you had before. Since this is a harmonic oscillator, we know how to quantize a harmonic oscillator. These are the eigenvalues of this matrix are the frequencies. So you have a frequency that is square root of these eigenvalues, and then you can compute the 0-point energy. So you compute the ground state energy. And this ground state energy, you can show that is a function of cosine, and this function is more or less cosine square again, as before. So again, quantum fluctuations, as thermal fluctuations, selects these states 0 and pi, these collinear states. Of course, in the quantum realm, these quantum fluctuations, they happen to be very strong around that transition between the Néel state and the stripe state. So there is a huge controversy happening here, especially because quantum Monte Carlo is very limited here. So what is the real phase that is happening here? People say that there is some sort of a gapless spin liquid here, a valence bond crystal, some exotic states of matter appearing here, and this is still an open question. It's still being debated. But far away from the transition region where frustrated is very strong and our approximation here works, we have the stripe phase and so on. There are many candidate materials for that. There is these materials, most of them, they have some ion magnet which is enclosed in an oxygen tetrahedra or cage of oxygens that that endows effective coupling, magnetic coupling between the magnetic ions. So you have a J1 interaction, J2 interactions, and depends on the many materials that you have here, you have a different ratio between J1 and J2. So here, J2 big, it would be the materials that has this order by disorder mechanism. But these nematic or stripe phase, as far as I'm concerned, were never seen in experiments, or at least not a very conclusive signature of these states in nature. So why is that? And maybe the model is wrong, maybe there are couplings to the other planes. These are 2D-like planes, materials that has weak couplings to other planes. So you can put you say that culprit is the other planes, the 3D character of the material, or the interactions that we are not taking into account. But I propose that there can be another culprit for that, which is disorder. So I will introduce the effects of disorder in this context. So what's the effect of a single vacancy at t equals 0? So you can do a Monte Carlo, cool down very low temperature, or do some other numerical technique and see what happens to the ground state. And that's the configuration of it. So you can see that is not the 0 pi or pi 0 state. It's actually a non-collinear state where we have a sublattice that is perpendicular to the other sublattice. So it's like pi over 2 is being selected. Instead of a minus cosine square, you have a plus cosine square. And this can be shown to be the case if you do perturbation theory. A wave-hand argument is like the one that we did before with these fluctuating fields. But with thermal fluctuations, the fluctuating field is like this. It's perpendicular to the direction of the spin. But if you put a vacancy, it's like you are shrinking the size of the spin. So the fluctuating field is not in this direction, but in this direction. So you multiply by pi, you sum pi over 2, the argument that I had before, and then you get a plus cosine instead of minus cosine. So a single vacancy, it actually favors this other state here that's called spin vortex state, because if you go around the plaquette, there is a vortex. And so we say that the O3 ground state accident degeneracy is lifted down to O2. Right? Because now it's perpendicular, I can do, still there is an O2 degeneracy to the left between these two sublattices. All right, that's what happens for a single vacancy. And the order by quench disorder mechanism, which was that just presented, statistical fluctuations of the size of the spin, selects the spin vortex state. So what's the result state at finite temperature? So at finite temperature, an entropic gain will happen in the bulk, because everybody is at finite temperature, that favors the nematic states. Locally, we just have shown that it's favored by, the favored state is vortex state. This vortex state is lifted from the ground state degeneracy because you remove some couplings out of the system. When you have a vacancy, you can think as you remove all the couplings around that vacancy. So it's energetic selection because you locally remove the magnetic energy content. So it's energetic selection. While this other state away from that is selected by entropy, it's an entropic selection, is in the bulk. So far away, of course, the bulk is huge. It's favored to have the nematic state. And only locally you tilt a little bit, so you alleviate frustration. Then you have a local energy gain that does not scale in the bulk. So you have a impurity that is screened. So here is a plot of this color plot, a heat map of this thing. Red means that you are in the spin vortex. Blue means that you are in the nematic. And so you have many impurities around, and they are screened. And the correlation, the screening length is related to the correlations either of this state or of that state. I will not go through those technicalities. But they are screened. So you would think that that's the whole story, right? You put this order, they screen the impurities, and you have a beautiful nematic state. That's not the case. I will now do a reload of the order by quench disorder mechanism. So far, we have considered only a single impurity. But what happens if I put two impurities, one on top of each other or one besides each other? This can happen with a chance. If you have a density x of impurities, this happens with probability x squared. So it is there. It can be very rare if x is very small, but it is there. So if you put two impurities, remember, you remove the coupling from here, remove this coupling, remove that coupling, and so the coupling is around. So what coupling is remained? Is the one, J1, between the two sublattices. So I want, energetically, what is favored? To counter-align the sublattices, 0 pi state, or θ equals 0 if you wish. But if the two impurities were on the horizontal line, I want to align the sublattices. Then I would have θ equal pi, or pi 0 state. But these are nematic states. So the order by quench disorder, if a single impurity appears there, it favors the spin vortex. But if two impurities appear together, they favor the nematic. But they break the symmetry between the nematic, because this one wants the θ equals 0 and this one wants the θ equal pi. So locally, these impurities are breaking the nematic symmetry explicitly. So it's an energetic gain, it's not entropic gain. Again, it's an energetic gain, but on the other state, on the nematic state. So this order is doing lots of stuff. It's doing that spin vortex stability that we have just shown. But when you put more impurities, they come together and they can favor another state, nematic state. Wow, okay. So what would be the effective model for the nematic degrees of freedom? Suppose I have a very few impurities. As we have seen, they are screened, right? Here, they are all screened. So forget about the impurities. They are screened. The bulk is in the nematic state. But maybe somewhat here, because this is very few impurities, maybe somewhat here, there are two impurities together. They favor the nematic, but locally, which nematic, the vertical or the horizontal? Well, it depends if they are vertical or horizontal. So the effective model for the nematic fluctuations is, again, our Ising model, but with random fields.
Sorry, to happen this other mechanism that you're talking about, the two impurities must be really, let's say, adjacent to each other, or they can be into the screening volume of one of the two?
No, they have to be one besides each other.
Okay, so
Because
if you have two impurities that are in the screening regime of one of the two, they don't do this phenomenon.
No, they only do if they are nearest neighbor.
Okay.
Because it's an energetic selection
yeah.
in the following sense. You need an imbalance between the J1 couplings, horizontal and vertical. Here I remove 1, 2, 3, 4 horizontal couplings, and while I remove 1, 2, 3 vertical ones. So I need this imbalance. And from field theory, there is a simple way to see that, which is the following. These stripes on nematic state, as I just showed you, it breaks the real space symmetry, the Z2 symmetry between horizontal and vertical. So does this order. This order also breaks real space symmetry. Of course, the first symmetry it breaks is translational. But a single impurity does not break the vertical horizontal symmetry of the lattice. But the two impurities, one near each other, does that, or vertical. So by symmetry grounds, we expect that these impurities, this pair of impurities, couple to the nematic order parameter. So the effective model that we expect is this one. As the impurities are isotropic, the average value of this random field is 0 because I have as many horizontal and vertical pair of impurities. So I have as many favor nematic 0 pi or pi 0. Okay? But there will be a fluctuation. It's 0 mean, but has a width. And this width is proportional to x squared, the density of impurities. So if x is very small, do we care about that? Do we have, is this really important or not? And the next slide will show you that no matter how small is x, it destroys the phase transition. It destroys the order state. It destroys the nematic state. How can we see that? So let's go back to the old good easy model in a field. Zero mean field. The field has 0 mean, it's a random field, but has a width. The argument comes from these two gentlemen, Earing and Ma, and they propose the following. They were doing a proof by contradiction. They will assume there is another state and then arrive in a contradiction, or at least a criterion for contradiction, let's say. Then they will have a criterion. How is the reasoning? Let's go to t equals 0. No thermal fluctuations. Forget about thermal fluctuations. I will assume that there is a ferromagnetic state, and let's say that the symmetry was broken up. All right? So if I plug this state into the Hamiltonian, I gain energy, the exchange energy everywhere. But when the field is aligned, I gain this energy, but when the field is counter-aligned, when H is negative, I lose energy. So they propose the following. Maybe if I put a domain of down spins here, I can gain this energy that was up. And here, this region was mostly fields down. Because then I gain the Zima energy here. But okay, so this can happen. We can see if this energy is lower, if I can lower the energy and get a better state. And I will do this in a size of L, and to see what's the optimal size of L for this domain here. So the first thing that we know which will happen is the energy will certainly rise because you have a mismatch of couplings around the area. So there is a domain wall cost, which is proportional to J, all the J's that are in the area of this volume here. So L to D minus 1. But as we just said, I may gain energy here because mostly there is a fluctuation, the fields are most down here. So what's this energy gain that we typically gain? We have to look at the fluctuations of this field here, or the sum of this field, because all spins here are down. So I can get this sigma I and get out of the sum, and I have to look at the fluctuation of the sum of HI. So HI is a zero mean and finite width. And when this L is very big, I'm summing lots of random variables. And the statistics of the sum of lots of random variables is governed by the central limit theorem. And the central limit theorem says that the fluctuations increase with square root of the volume of the square root of the number of random variables, and the number of random variables is the volume. So I get L to D half. So if I compare these two energy gains, I have that the domain increases. I mean, I gain energy if I increase this L up to infinity if dimension is less than 2. So in dimensions less than 2, I cannot have another state because I can just simply nucleate a domain and increase up to infinity, and that state has less energy. So how about the D equal 2? And then comes these two other gentlemen here, Greenstein and Ma, that says that this also works for D equal 2. These arguments too simple to look at the critical dimension, D equal 2, but they conclude that this also happened for D equal 2, so meaning that the lower critical dimension of the problem is 2. No transition at all. So you don't have a dematic state is destabilized by this impurity. Doesn't matter how rare they are. And then we do Monte Carlo with 1% of impurities. And well, that peak that was developing the specific heat is not there anymore. The magnetization, I increase the system size, it decreases. The nematic, or the parameter, I mean. The binary cumulant, I see no crossing. And the susceptibility, I see no peak or something happening. If you do some heat maps of these other parameter, you compute locally that other parameter for the Hamiltonian, you see that there are some regions where you have negative nematic order parameter and some regions that have positive, and the system is broken into domains. That's what happens when you are at or below the lower critical dimension. You don't have the entire order through your sample. You break the sample into domains of local orders. All right. So the conclusion so far is this. At the clean case, without any impurities, you have a transition between a paramagnet and a nematic state for high frustration. But as long as you put impurities, this nematic state is destabilized, and you don't have a state. There's a paramagnet here as well. So you have a paramagnet everywhere. Questions? How much time do I have? Yeah.
Yeah, so I have this question regarding the phase of the J1 over J2 greater than 1, or the phase of J2 divided J1 greater than 1 are the same, right? Because the model is invariant under the changing J1 and J2, or I'm missing some point here.
No, no. J2 and J1 do not commute this. When J1 is small, you have one sublattice only.
But you have two lattices, right? That are
I have one lattice, actually. If I remove J2, I have that lattice, and that's it. Now, that was Nathan's question, right?
So
remove J2. You have one sublattice, and that's the simple Néel state. Now remove J1 and leave only J2. Now I have two lattices, interpenetrating lattices, which do not talk to each other.
Okay, I understand that. But my question is, suppose that you give me that Hamiltonian and I exchange J1 and J2. There is
nothing happens. Yeah.
Okay, so
I mean, nothing happens. It's totally different, right? You go from this side to another side. This side you have this microscopic O3 accident degeneracy, and here you don't have it.
Okay, so yeah, because my question was, I'm thinking like the physical dynamics in this phase. So in the quantum case, you mentioned that you will have some spin waves, right? So you will have in the diagonals, you will have anti-parallel spins. So if you change one, you will have wave moving in the diagonal, wave moving in the other diagonal. But that will also change the, let's say the configuration in the vertical, in the horizontal lines, right? So you will also have like waves moving in the horizontal lines. My question was, for me, it's like in this phase you will have like two independent spin waves that will not, let's say, interact. But in the opposite phase, you will have like the same phenomena, but it's changing the horizontal direction by the diagonal ones. So it's what I wanted to ask.
Here, yes, you have the spin waves in that direction, in this direction, right? Here you have in that direction, in this direction, but you also have another one in this direction and in this other direction. But then if you couple by J1, the spin waves will scatter.
Okay.
And there is an optimal angle that the scatter will be less than your diminishing energy.
Okay, I see. And regarding the effective model that you use for the defects, for the Plaquet defects, the M parallel order parameter.
The vestigial order parameter, yes.
So that at the end, the effective model is the one of a Ising spin with a external field, right? So if you put like a background of your vacancies, what I will expect is that you will have like a spin glass model rather than an Ising, because you are putting like a kind of random vacancies with some kind of density, so that will like affect the couplings. But why do you choose the add like an external field rather than putting that model decision with a spin glass?
There is no spin glass in 2D.
Okay.
There's practically a theorem showing that. And the resulting state, you may think that it resembles a glass because of these, right? For instance, let's go to this temperature here. Then you have a blob here, a cluster that is mostly in the up nematic direction, 0 pi, and another cluster that is in pi 0. So these would resemble like a glass. It's locally ordered, but disordered in space. So this is your glass, but I do not call it a glass. I call it a paramagnet. Why is not a glass? Because there is a single ground state. The field here is, you see the sticks here, these sticks means that the two vacancies are horizontal. So mostly the fields here are horizontal, so they know that this blob, this cluster here has to be in the horizontal nematic state, and here is in the vertical nematic state. A glass would have many degenerate ground states, but there is only this one. You need random access to that, and that's the next model. Then you have, for instance, imagine that maybe I did not emphasize that, but when you put the random field, the O3 ground state degeneracy is lifted down to G1. So that's why you have a unique state here. But now suppose that you have random access instead of random fields. Then the state here would still have some degree of freedom because access, let's say, up and down in this direction, and here up and down in that direction. So you have still a remaining entropy of log 2 here, remaining entropy of log 2 there, and log 2, and then it's a huge entropy that is still there. And the interactions, you barely lift this degeneracy, and then you would have a glass because you have many minima. Okay. But that's the next one. Okay, so we're done. I don't have to go to the next one. Actually, I think I cannot, right?
If you want to go a little bit further, if it is confined in a decent amount of minutes, yes.
I don't know, maybe just to flesh out. You can give it just to flesh out the nice pictures that took me so long to build, right?
Yeah.
So the model is like this. This easy plane paracloth, for instance, like erbium titanate. It is XY spins. Actually, there is the Z component, of course, but due to the crystal lattice, the Z component is practically forbidden. It's high energetic if the spin flips to the Z direction. And the Z direction actually are those arrows here. So the model is written in the X, Y, Z in the local reference frame. So in this atom here, the local reference frame is this one, Z is here, and point in that direction. And it looks like this. So there is X, Y, X, Y interactions and off diagonal interactions, X, Y, and Y, X. And these couplings are parameterized, and this is, well, this is hard work of quantum chemistry. You have these phases that depends on the axis that you are looking at. So at this axis, this phase is 0, there is there, and so on. So that's a huge mess, and this is also frustrated magnet. Because for instance, if you look at the interaction between 0 and 1, I put 0 here, I get X favor, or actually Y favored. But if I go to 0, 2, then I get X favor. So I cannot put this guy here either in the X or in the Y in the same time. So there is frustration as well. So the symmetry of the problem, you can rewrite that Hamiltonian in I suppose in a better way or in a more familiar way, where you have the Heisenberg-like interaction here. But because of those X's and those phases, you have something that is not Heisenberg-like. It doesn't have O2 symmetry. It has only Z2 symmetry. Only if I make theta plus pi. Then I get the Z2 symmetry. So the interaction symmetry is Z2. But if the system is, well, because the system is homogeneous, well, if there is no impurity, these three X's, they are all the same. So you can do an extra exchange of these X's, and you get enhance of Z2 up to Z6. Now, if you go to erbium titanate, alpha is between 0 and 2, and there is again, because frustration, there is this accidental degeneracy. You can point out the spins everywhere in the plane for any theta, and the ground state does not depend on theta, just like the model that we had before. It's just constellations that appear because of these three axes. Basically, because you're assuming cosine in a circle and it sums to 0. So there is a huge degeneracy here. If you put thermal fluctuations or quantum fluctuations, guess what? That O2 accidental degeneracy is lifted down to Z6 which is the symmetry of the interactions furnished with the symmetry of the lattice. So if you are here, you either favor one of these axes. If you are here, you favor either of these other axes here. So there is a phase transition, and don't ask me why they call this state psi 2 and psi 3. I don't know why these names. But this is measured experimentally. So we know it's there. So if I put this order, what do I do? That enhanced the symmetry, that was because these guys were there, are lifted by this order, because this x is not equal to that anymore. So if you compute, if I put a defect here, I can compute the difference energy, and this different energy depends on the configuration where I am. I can either favor the psi 2 or psi 3. It's like I'm now again in a random field situation where I favor either psi 2 or psi 3. But psi 2, psi 3 is not I do not, the degeneracy is still Z2 because of the interaction. So meaning that I will choose either this direction or this direction or this direction, but I still have an axis, so I can flip pi over 2, I mean by pi everybody, right? And still have a remaining entropy. So this means that I have to crank up this order a lot, so I can indeed go to the cluster spin glass phase as was before. And I'm in D equal 3, so the random field argument doesn't play because I'm above the lower critical dimension, now D equal 3. So I can still have the other states at finite temperature. And there are experiments that see this mosaic of psi 2, psi 3 for high concentration, so it corroborates our predictions. And well, that's what I had to tell you. Sorry for passing a little bit of the time. Thanks for your attention.
Thanks a lot, José, for this lecture. So we have questions?
Yeah, Nathan has...
Yeah, sorry.
What are the defects in this real physical system? How do you create a defect, or what is it?
Yeah, you remove a magnetic ion and put a non-magnetic one, so you dope it.
And that removes the spin from the site? Is that right?
Yeah, then you get a vacancy. Experimentalists will not admit that to you, but there are impurities in the crystal lattice, and these impurities, they may happen to distort the orbitals, so you get a bond disorder as well. So the J's become disordered, not only vacancies.
More questions? Yeah, two. One there, one there.
Yeah, thank you for your talk. Maybe this is a low blow, but I'm following Nathan's question, which is, how do they manage to experimentally freeze the impurity? Because at first, I thought they would move around, right?
What move?
The impurity, or...
No, the impurity is static, right?
So how do they manage to, do you know? It's just,
yeah,
maybe it's a low blow.
You have the crystal lattice, right? Let's come back to those. Here. So you have, let's say, the oxygens are the red ones. Molybdenum would be the magnetic one inside this cage. But then you remove, when you are preparing your sample, you remove some molybdenum and put a non-magnetic ion that has the same size. So they fit there and do not distort the lattice too much, or practically nothing. So there will be no magnetic ion here, so you have a vacancy.
Yeah, but there is no bonding anymore also, right?
Yeah. But then
simple to...
it's a vacancy as we drew in the pictures. Yeah, just remove a spin.
Okay.
A site. Yeah.
Hello. You showed that you don't have long-range order for dimensions equal to or less than 2, right? Do you know if there is some relationship with the Fourier scaling for localization, for example, where you don't have extended states for d equal 2 or less than 2? There is some relationship between these conditions?
You said lots of things here, right? We do have a magnetic order in 2 dimensions if the symmetry that's being broken is discrete. The thing is, the resulting order state, now we have fluctuations or energy modes that will propagate through the system. In this disordered environment, since it's 2D, this fluctuation will propagate, and the effective model for them would be something like an Anderson model. Then the fluctuation could be localized, but it's the excitations, that's the correct word. The excitations could be localized. However, in these magnetic models, most of the excitation has bosonic character. And only at the very, since this is discrete symmetry, these excitations are also gapped. We have seen in other models that if you can break continuous symmetry, then you have Goldstone modes. And except for the zero energy Goldstone mode, everything is localized, even the Higgs modes. So yes, you're right. Then the excitations of this model would be localized, but you do have that crystal magnetic crystal.
More questions? Okay, if not, we can thank Jose again.
Thank you.
Can you elaborate, because there are things that are not clear to me.